So I'm counting on your patience. I feel fortunate to be able to kind of run through this with you, but this is kind of a new way to do review sessions for me. So I think it's kind of fun. But if there's some kind of bumps along the way, just go with me. I know you will. So in chapter 2, among other things, and it made it to your review sheet, so that means it made it to your unit exam, is just kind of that general concept of the Milky Way that we see in the nighttime sky. And that's kind of a band of stars that goes from horizon to horizon. And so this figure from your textbook actually kind of shows you, when we look at the Milky Way, what we're actually doing is looking into the plane of our galaxy. And the reason it looks milky white is because we're looking at tiny little stars. They're tiny to us because they're so far away. It's equal to lots of stars. And actually, that was one of the things that Galileo used his telescope to look at the Milky Way. And he's like, dude, that's not like gas and dust or fog. That's actually stars. And so those stars must be very far away to be that small. Let's see, the next term is circumpolar stars. And by definition, a star is what we say circumpolar if it never sets below your horizon. And you're going to see here on the review slide, I kind of said these circumpolar stars make a bullseye with Polaris, okay, which is the North Star. Now, but not all circumpolar stars are close to Polaris. So, for instance, if you are and you guys had a homework question like this, if you are at the North Pole, okay, if you're at the North Pole, then Polaris is right overhead. It's at what we call your zenith. Polaris, the North Star, is. So if you make the bullseye, basically you get bigger and bigger circles around Polaris, and then at what I'm going to say, and this is what you probably said in your homework, is all stars are circumpolar if you're at the North Pole. So with regard to being close to Polaris, no, the stars are not close to Polaris. Okay, so constellations, general facts. So one of the things I said in lecture is to know that we have over time, we currently have chopped up we have chopped up the nighttime sky, the stars in the nighttime sky, into 88 sections. Now, those sections aren't necessarily equal, but we call those sections constellations, and we have made different pictures in those stars in those boxes. One of the things I think would be interesting is, like, thousands of years from now, do we still have, do we kind of subscribe where we live in our culture to the Western tradition of naming pictures in the sky, stars. Okay, so constellations, general facts. Celestial sphere, key aspects. So, yeah, I deleted it. I wrote it down and deleted it back. So I'm going to go ahead and throw up a celestial sphere up there. But remember, the celestial sphere is a good model to kind of show how the stars are kind of stuck together in these 88 constellations. The key features, remember, I was looking for in your homework were the celestial poles extending from Earth's poles and the celestial equator extending from Earth's equator. Plane of the ecliptic. I went ahead and snagged an image from the internet to kind of show you again what the plane of the ecliptic looks like. We can think of the ecliptic as kind of imprinted on that celestial sphere, but what I prefer to do is kind of step outside that model and just simply think of the ecliptic is the plane that holds the Earth as it orbits the sun. Okay, and notice then in this figure I got from the internet that it also the ecliptic also holds the path of the other planets. So we end up with this kind of frisbee-looking thing as our solar system. The next one, we see different constellations throughout the year. And I kind of, in green here, want to remind you that it depends upon your latitude. Remember, latitude is where you're at relative to the equator. So I think your textbook did a good job here. You kind of see left and right. The left one is somebody, again, at the North Pole. And the right is actually somebody that is a latitude south of the equator. And that light blue there are those people's local sky. Okay, so The constellations that you're privy to have to do with where you are relative to the equator. So the next thing is that seeing different constellations throughout the year. Now this was a figure from your textbook, and I apologize, it's really small here, but hopefully it will jog your memory that actually that little yellow thing in the middle is the sun, and that blue line, that's that blue circle that goes going around that yellow thing, that's the path that the Earth takes as it orbits the sun. And then kind of that that yellow there, that yellow circle out there, actually would be the path, I think this is right, that kind of showing you the background, where the sun is relative to the background stars. So actually, again, I'm going to have to refer you to your textbook because I can't tell it, but those little dots there are making up constellations that are those special zodiac constellations. Okay, so as the Earth orbits the sun, the constellations we're going to get to see at night are going to change. Okay, and the sun is going to appear to pass through constellations. Of course, we can't see it because the sun's so bright. Different constellations, and that's where you get your sign. So I think that's pretty cool, even though I'm not really into astrology. Okay, the next one is a big one, and I didn't spend a whole lot of time on it. Okay, but if anybody asks you why the Earth goes through seasons, why we have winter, then we come out of winter and go into spring, and then we go from spring into summer, and from summer into fall, and from fall back into winter. It's because the Earth is spinning on an axis that is tilted, and it's tilted 23.5 degrees from, I like to think, being perpendicular to the ecliptic, the plane of the ecliptic. So the Earth's axis of rotation is tilted. If it weren't, we would not have seasons. So this tilt, now this is kind of a, what do you call it when it's a misconception. This tilt doesn't give us seasons because sometimes we're a little bit closer to the sun because we're tilted. The tilt gives us seasons because, as you see down there, directness of the sunlight varies throughout the year. Okay, so the tilt has consequences with regard to the directness of the sunlight. The tilt also has consequences with regard to the number of hours of daylight and nighttime, and we kind of talked about that in lecture. Okay, then we get into our precession. Okay, so I use the word coning. The precession is basically the Earth's axis of rotation stays tilted, but it kind of cones or kind of spins around, kind of like a top kind of wobbles as it's kind of, when you start a top, it's like straight up and down, but after a while it kind of loses some energy and it starts to kind of wobble. That's what our Earth's axis is doing. But it takes, did I put the time down here? Yeah, in purple up there. How long does it take to complete one coning movement? And that is 26,000 years. So as it cones, it points to the North Pole points to a different pole star. Okay, it won't always be Polaris. It won't always be our North Star. It's been Vega before. If you're familiar with, remember, Vega is in the constellation Lyra. Beautiful, intense blue star, part of the summer triangle. But Vega used to be our North Star. Okay, but it's such a subtle thing, we're not going to tell it. You know, I kind of smile because if you remember, that actually in the southern hemisphere they don't have a pole star. So one of my things is during this coning, you know, maybe they get a pole star and we don't. Anyway, okay, Polaris. Polaris, the current North Star, we can actually, and navigators have used it for a long time now, to be able to use its location to gauge where you are with regard to your latitude. How close or far away from the Earth's equator are you? And I just kind of look at these two extremes. The two extremes with regard to being at the equator, that's the top one, or being at the North Pole or one of the poles. I guess it'd be the North Pole. Okay, if you're at the equator, you look for Polaris. and you're going to look due north, and just picture that. If you're at the equator looking due north, you're going to find Polaris, but it's going to be like on the horizon. And if you're, we talked about this a minute ago about circumpolar stars. If you're at the poles, you're going to look for Polaris, and it's going to be right overhead if you're at the North Pole. So this kind of gets me to, like I started to say, what navigators have done for a long time now. You can actually, and I'm going to correct this, you see where it says latitude? It should be altitude. You can use the altitude of Polaris to tell your latitude. And the reason altitude is wrong is, remember, sorry, what latitude is wrong. What altitude is basically you put one hand out at the horizon and you put the other hand where the object is, and where that angle between your two, I should say, arms. You put one arm out to the horizon, one arm up to where the object is, and what that angle is between your two arms, that is the altitude of the object. Okay, so, and it was explained with regard to local sky. So if you're at the equator, okay, you put your two arms out, you put your arm out the horizon, you put your arm out where Polaris is, and your angle is 0. If you're at the North Pole, you put one arm out at the horizon and one arm up at where Polaris is, and you have made a 90-degree angle. So you're at actually 90 degrees latitude. So kind of finishing up here, we have Perigee and Apogee. Okay, Perigee has to do with the moon being closest to the Earth, and apogee has to do with the moon being furthest from the Earth. And it's kind of similar to perihelion and aphelion, isn't it? Okay. Oh, see, I have a typo. Let me see if I can go back. Because I have closest to the sun, and it should be furthest from the moon. Dang it. Furthest from the Earth. Perigee and apogee have to do with the Earth-Moon system. So let's see if I can fix this so we're all kind of on the same page. Okay, so what I want to do is change that furthest from the Earth. Okay, good. Alrighty. So just kind of finishing up, and I apologize because I think my videos are going to kind of have a little caption over this, but you want to, for your unit exam, be familiar with eclipses, okay, and what you're missing right here, over here in the kind of the lower right hand corner, and I'm going to fix this later, is that we can have an eclipse of the moon if the moon is in its full phase, and kind of the nodes line up and stuff like that. But you can only have a lunar eclipse when the moon is in its full phase, and you can only have an eclipse of the sun when the moon is in its new phase. So kind of up here at the corner, I was running out of room, I wrote to kind of remind you that there's different types of eclipses. Both lunar and solar eclipses can be total or partial. And then just specific to solar eclipses, we have that special annular eclipse. Okay, and that's penumbral. You can't see that very good. There's a with specific to lunar eclipses, there's something called a penumbral eclipse. So just to kind of give you a little bit of ease, I do not test anything this semester over an annular solar eclipse, and I don't really test over, I think, total and partial eclipses, but I do want you to understand a little bit that the when an object, I should say, when the Earth or the moon casts a shadow, there's the umbral part of the shadow, and then that's the deepest, middle of the bullseye part of the shadow, and then there's the penumbral part of the shadow. So I hope this helps.